Hello, and thank you for reviewing our presentation today. Today, we are going to be presenting our project for EAB review. Our project was the fish passage at 61st Avenue Northwest. And just a disclaimer, this is a student presentation, and none of this reflects St. Martin's University and should not be substituted as professional engineering. My name is Hayden Lampers. I am the structures lead, a co-project manager, and the co-CAD designer. My responsibilities include the sub and superstructure calcs, keeping track of our deadlines, and drafting a majority of the plan set.
My name is George Caballero. I am the roadway lead for the project. I am also a co-project manager. My responsibilities included researching and implementing the roadway guidelines, the detour plan, guardrail details, and our traffic control plan.
My name is Zachary Martin. I am the geotech lead, as well as a co-project manager, and I'm helping Hayden with the structure design. Some individual responsibilities I have are site preparation, slope stability, and grading.
Hi, I'm Danielle Miller. I'm the environmental lead for our project, also co-CAD designer and project manager. I research the environmental aspects, water resources, temporary erosion sediment control, and helped with the presentation lead. Also did the stream design research.
Our senior design team was tasked by Thurston County to design a replacement for the existing culvert located at 61st Avenue Northwest near Fry Cove Park in Olympia. The site is characterized by a wetland situated north of the road, which feeds a stream flowing through the existing culvert before discharging into Fry Cove, part of the Eld Inlet. The current culvert measures at 120 feet in length with a 72-inch diameter and has been rated by the Washington Department of Fish and Wildlife as only 33% passable for salmon and other aquatic species. Additionally, the culvert has a documented history of maintenance issues as large sediment and debris cause blockages.
The team would also like to acknowledge the Squaxin Island tribe. This project is on the same land as this tribe, and we would not be able to do this project if their land was not taken from them. The team would like to acknowledge the indigenous people who have stirred this land since time immemorial and who still inhabit the area today. The Stichas Band of Indigenous People of the Squaxin Island tribe, we recognize you.
All right, as George already mentioned, the main purpose of our project is to replace the existing culvert with a new structure. This new structure will need to allow fish like salmon to be able to swim up and down the stream, as well as other aquatic species that live in the stream. Our other goal with this structure is to have it better handle debris. There's a lot of woody debris to the northern side of the site that flows down the stream. So allowing that debris to pass through would help Thurston County with their maintenance costs. Some just team goals we have during this project is to work with Thurston County and other mentors, as well as to keep other stakeholders like those listed on the slide involved in the process. This is some pictures of our site visit in the fall. In the top right is the northern side of the culvert where the stream enters, and the lower left pictures are the southern side of the culvert, which is where the stream exits the culvert and flows down towards the sound. The bottom right is 61st Avenue, which is what the stream flows under. And then the top left is the plan set that we were given from Thurston County about what's existing on the site. During our 30% design phase, we completed multiple different things. First, we did an alternative analysis. Then we did a cost estimate based on that. So we looked into regulatory compliance and permits, created an initial plan set, and also researched sustainability for our site. So for our alternatives, we compared 4 different things: do nothing option, a no slope culvert, a concrete box culvert, and a short bridge. With those alternatives, we created this chart shown in the slide and ranked all of the alternatives based on how well they met the parameter. Then through scoring, we found that the short bridge option was the best option. We decided to go with that.
Three important socioeconomic factors were already addressed in our design, including equity, economy, and the environment. Skipping to the environment, the bridge was adapted for future climate change. Um, how was it? So, according to the Environmental Justice Index, the site which our bridge will be constructed on has a climate change risk between 50 to 80 on the national percentile scale, so it will need to be accounted for. But our bridge can already sustain a floodplain utilization ratio of 3. And for context, the existing site the existing design was planning to address it at 2.2, so it well exceeds those requirements. The construction of our bridge will also account for the environment. The erosion and sediment control BMP, or best management practice, will be addressed and accounted for by using silt fences and check dams to prevent erosion from going into our tributary.
For the 60% design of our project, we split into separate groups and separately worked on the structure design, sub and super simultaneously. We split into stream design, pavement design, and design of guardrail. I was personally in charge of the superstructure design, and through various hand calcs and Excel calculations, we came up with a deck depth of 8 inches, which is found by comparing concrete depth calculations with the AASHTO LRFD minimum requirements for steel girders. We came up with a barrier type of 34 inches single slope based on crash tests listed in the LRFD as well, and we applied limitations that are respective to our site. We ended up coming up with 5 steel girders size W36-182, and this was found by using dead and live load analysis using HL95 heavy vehicle loading and AASHTO LRFD load cases. We then compared the max shear, max moment, and deflection, and compared that with girder capacities. This here is a section view of our proposed bridge. So we've got our girders there, the deck, and that's a 2% grade for the roadway. We've got the dimensions of our barriers as well as plans for the future. We have not detailed the rebar for the deck or the barriers quite yet, but that is in preparation for the next design phase.
After we completed the superstructure design, we started looking at the substructure and we realized we had a little bit of a problem. With the current length of our bridge only being 30 feet, there's not very much room down by the stream for the soil coming up from the stream to gain height, since it has to be at a slope of around 2-to-1 ratio. This is a problem because the footing for the abutments needs to be under that soil. Otherwise, the stream will erode away at the soil underneath the footings, which is a very bad thing. So because of that, the footing needs to be at about level with the stream height, which is around 25 feet below the roadway. That means our abutments are around 25 feet tall, which becomes a problem due to the amount of soil load that's pushing on the wall. And on top of that load, there's also the axial load from the bridge itself. So it's a problem with buckling. And then you'd also need very large footings for that, which is going to extend out in towards the stream. For example, I found a WashDOT standard plan for a 25-foot tall retaining wall, and that footing was around 14 feet wide with a toe width that stuck out 4.5 feet from the edge of the wall towards the stream. So yeah, that doesn't really work. We are coming up with some solutions though. First off, we could have obviously increased the length of the bridge. That would allow the abutments to be much shorter, maybe like 10 feet tall instead. I'll show you why in the next slide. Another solution would be to use ties or anchors to resist that lateral load from the soil. A similar solution is the geosynthetic wall, which again ties the soil back so that it's not pushing on the wall. We are currently leaning towards doing the geosynthetic wall. However, we'll still have to create a footing for that, just due to the axle load, which has the potential to decrease the amount of space we have for the stream. So we'll see where that goes. Next slide. All right, this is our current elevation or profile view for the bridge. As you can tell, the substructure is not really accurate because of what I said in the last slide. However, the superstructure is accurate with our barriers and our I-beams, as well as an approach slab leading up to the bridge itself. The slope of soil that I was talking about is what goes from the edges of the stream up towards the abutments. And as you can see, the toe of the footing needs to be below that soil slope.
So now that we have talked about the superstructure design, I will now talk about the hydraulics or the stream design that we use to design our bridge. For reference, here are the manuals, codes, and models that we used. This slide shows what was happening at the existing corrugated pipe. This is the stream velocity based on the existing conditions. So let me call your attention to the diagram on your left. The columns with the red headings represent the stations downstream of the pipe, and the columns with the green headings represent the stations upstream of the pipe. This being upstream, this being downstream. What is this diagram showing? So if you notice the two variables in the white, Manning's N and the slope, we use this to calculate the average velocities for different flooding events. It was determined at the time that the slope was 0.07 or 7% based on the difference in height and length of the existing corrugated pipe. And we used a Manning's N we determined to be adequate. We found that the average velocity during the 100-year flooding event was around 9 feet per second, and this was actually very high for our target fish population. But why? Let me give you some context. So the salmon and trout we are trying to build this fish passage for include some specific species, including the endangered and threatened steelhead salmon, coho trout, and cutthroat trout. Excuse me. Here's what we know. According to the culvert design for aquatic organism fish passage manual, the trout can only travel against a flow of 4 feet per second on average. The steelhead salmon can travel against a flow higher than that. But because we wanted to be conservative, the target average velocity we wanted the flow to be was 4 feet per second. And what do I mean by that flow? I mean the flow coming out of the end of our stream. So from all the way upstream to all the way downstream, we want that flow to be 4 feet per second. Moving on to the next slide, what was changed to try to make this average velocity happen? Well, we have tried to make the slope different. How did we go about that? We decided to change the project reach, so where our stream design starts to where our stream design ends. And here this slide shows what stations we started with and what stations we ended with to get that change in distance we were looking for. So We now have a slope of, instead of 0.07 to a slope of 0.008, keeping our Manning's n the same. We determined that the 100-year flow or flooding event gave us an average velocity along these gave us a excuse me gave us an average velocity around just over 4.5 feet per second. Next steps, we'll be looking at how to drop this down further with the proposed stream design cross sections. Next steps, we'll be looking at how to drop this down further. Let's look at the proposed stream design sections we're thinking about. So this design shows the flow area for the stream and not the fill itself or the soils itself, but just the flow area. If you were to take a cross section of the stream, what it would look like. We wanted to go for a trapezoid shape, so these dimensions shown on the slide account for the average water depth each type of fish needed, which was 1 foot continuously throughout the stream. This data coming from the fish characteristics, for Washington State Department of Fish and Wildlife Fish Characteristics Manual. The slope along the side is 3 for reference. Overall, the variables considered to implement this preliminary design flow area include the following: the peak flow being our 100-year flow, the project reach, our distance, and the Washington State Department of Fish and Wildlife fish characteristics.
The first step in the transportation design process was modeling the existing road so that we could create our typical roadway cross-section. This road is classified as a collector by Thurston County, and so we use the pavement design structure for that road type from the Thurston County road standards. Our typical roadway cross-section shown below will adhere to the geometric pavement specifications outlined in the Thurston County road standards, with the exception of the 6-foot shoulders, as our site visit and topographic data confirmed that this roadway does not have shoulders. Our team consulted with Thurston County to identify a feasible road access solution during the project's construction phase. Initially, a temporary bypass road was considered. However, a detour route near the site proved to be more feasible as it has low mileage impact on road users. The proposed detour involves closing access to 61st Avenue Northwest and routing traffic along Young Road Northwest and Boardman Road Northwest to maintain access to residences in Fry Cove Park. We use Google Maps to compare the existing detour routes, and the travel time to Fry Cove Park via 61st Avenue Northwest is 3 minutes, whereas the proposed detour via Young Road and Boardman Road increases that time to 4 minutes, resulting in only a 1-minute increase. And since the detour route results in only a minor increase in travel time, the impact on residences and park visitors is relatively low compared to the logistical challenges of constructing and maintaining a temporary bypass road. To enhance safety of road users along 61st Avenue Northwest, guardrails will be installed and connected to the bridge's concrete barrier. Our team selected Type 31 beam guardrail per the WSDOT design manual for new installations at each bridge approach. Per the WSDOT design manual, the minimum guardrail run length shall be 75 feet and the guardrail height will be 31 inches above the pavement. Given that the existing roadway has no shoulders, the guardrail design and placement will follow case 4 from the WSDOT design manual, which requires construction from the face of the guardrail to the slope breakpoint. To ensure safety and minimize disruptions during construction, a traffic control plan will be developed and implemented throughout the project's construction period. And this will include details for detour signage and road closures, traffic control devices and safety measures, access for residents and public notification, as well as construction scheduling and speed reduction if necessary.
Here is our updated construction budgets with the quantities found from our 60% design, So for example, our steel girder value was changed, our concrete value was changed. So our updated budget is 2.5 million, which is lower than the original, which was 2.9. We still have our contingency of 40%, mobilization of 15%, bonds and insurance of 1.5%, and tax of 8.3. The only thing that is expected to change for the 90% is some little bit adjusted quantities, as well as impact of the tariffs that have been in place as of now. Some of the project risks that we considered are construction risks, such as machine or equipment failure, adverse weather, and tight work windows to protect the salmon habitat. We have some budget risks that we considered, including design changes, increasing the costs, the tariffs mentioned before, as well as the $2.4 million being slightly more than the $2 million. This is expected to get a little closer to the $2 million as we progress with our design and come up with more concise values for our quantities. We considered environmental risks such as the beaver dams up north breaking and some permitting. And lastly, we have considered the engineering design that we mentioned before with some unforeseen design challenges causing some cost disparity and design disparity.
Looking at our design schedule, as of April 4th, our team has completed all of the 30% and 60% design tasks. Moving forward, we plan on presenting at Scholars Day on April 29th, and then moving forward with the 100% planner report and 100% presentation. The next steps for our project moving into the 100% design phase include detailing the 8-inch concrete deck for longitudinal and transverse rebar in accordance with the WSDOT and AASHTO requirements, detailing the connection between the girders and the abutment cap, proceeding with the detailed design phases, refining structural and hydraulic elements, and assuring alignment with Thurston County and regulatory standards, conducting further geotechnical and hydraulic evaluations to optimize foundation design and construction methods, completing the stormwater pollution prevention plan and a list of best management practices that comply with it, and determining the slope percentage to get the average velocity below 4 feet per second. Here are some literature that we cited for our project. And just as a reminder, all of our documents will be linked in the Google Drive that is attached to this presentation. And that's all we have for today. We'd like to thank you for viewing our presentation. We are ScaleUp Solutions. Thank you.